This is my physics lab 4 where we looked at oscillations on a spring. So for the introduction, in this lab we observed the energy principle and how it works with a mass oscillating on a spring. And the mass was moving in both the x and y directions. So we made a computational model and then compared it to the real-life motion analyzed in Tracker. And then we saw if the energy principle was true and if energy was truly conserved. So the energy principle states that change in energy is equal to your change in kinetic energy and change in potential gravitational energy and your spring potential energy and any other types of energies. So when we look at our tracker model, we had a video of a mass oscillating in the x and y directions, and we tracked the mass and got the graph of the motion as well as a CSV data file that we would later use in Glowscript. And then we can see that the x motion goes in curves like a sine or cosine graph, and we can find the period t from the data and use it in our Python code. So we can see here that from the tracker video, we have the x motion going up and down. And when we graphed the y motion, it was also going in a very similar pattern. And if we wanted to find the period t, all we had to look for is the time interval between one oscillation. So then when we look at the Glowscript model, we could see we had to make several changes to the code. For example, the ball's mass was 0.402 kilograms. And then its initial position and velocity were extracted from the tracker model. Then on the right here, we have our G constant, 9.8, and then the K spring constant and the L relaxed length of the spring were calculated using the formulas we already had. We could rearrange them, and K was calculated by doing 4 pi squared times the mass divided by the period squared, and we got 6.83 newtons per meter. And then the relaxed length was the stretched out length of 0.7 meters minus mg divided by k, and that turned out to be 0.123 meters. Then for the L and L hat, we did the ball's position minus the spring's position, and then the L length of the stretched out spring by the magnitude of L, and then the S was our L minus the L0. And then we had to change some of our energies. So our K energy, our kinetic energy, was 1/2 mv squared. And then our potential gravitational energy was just mg pointing in the position of the y component of the ball's position. And then the spring potential was just 1/2 ks squared. And then our total energy was all of those added up. Then here are several more lines of code that we had to change. The K initial and all of the other initials were just the initial K, UG, US, and E, which we defined before. And then we had our gravitational vector pointing down, and its magnitude was mg. And then we had our F spring, which is negative k times s, which was our change, L minus L0, pointing in the L hat direction. And then our F net was those two forces combined. And then using these forces, we were able to update the velocity and position of the ball with the exact same way that we updated them before. So we had velocity plus F net over m times delta t. And the position was updated by doing position plus the velocity times delta t. Then we had to update the spring. So the L changed, the L hat changed, and the S changed, but they're defined exactly like they were before. Then we had to calculate all our energy changes. So the K, UG, US, and E were defined exactly how they were before, but of course our velocity was changing and our S value was changing, so these were changing within the loop. And then our delta K, delta UG, and delta US were calculated by just doing the final minus the initial like we've always done. And then the delta E was found just by adding up all the delta K, delta UG, and delta US. So then here's a picture of our spring motion. The blue is our predicted motion, and the red ball moved in a very similar motion, and that was our actual motion from the tracker video. So if we compare the X position and the Y position, we can see that the model was in blue and the experimental data was in red, and the red looks not as smooth because we had way less data points, but you can see that it was a pretty good fit and they match up pretty closely. So for the first what does it mean question, it's asking, is the energy principle satisfied? And when we look at this change in energy versus time graph, we see that it is definitely satisfied because our total energy, which is in orange, is 0 the whole time, so everything cancels out. We can also see how the gravitational energy, which is plotted in red, and the spring potential energy basically mirror each other, and they're oscillating up and down. And then the kinetic energy is also oscillating and becomes smaller over time. For the second part of the what does it mean question, we made two estimates of the oscillation period from the tracker data. So we have our x position and our y position graphs right here. And from the x position, we got 1.646 seconds, and the y position was 1.519 seconds. So the percent difference was only 7.7. And this makes sense because they should technically be the same. So they were in fact really close to each other. So this was my physics lab on oscillations. Thank you.